Hello everyone, my name is Karin Wolff and I'm the Teaching and Learning Advisor in Engineering at Stellenbosch University. I'd like to give you a little background which will help you to understand what it is that I do and how I may be able to help you. I grew up as the child of an electrical engineer and an automotive chemist. I had a privileged science-focused schooling. However, I opted for an all-round humanities degree at the University of Cape Town. My first real job in 1988 was in film production, right at the time that celluloid was changing to digital. This was my first experience of the impact of technology on ways of thinking and working. With a moratorium on film and television production during the 90s, I then spent over a decade teaching technical and professional English in Germany and Japan. When I returned to South Africa in 2005, I started my first higher education job at a University of Technology during the merger phases on a brand new mechatronics diploma program. I taught engineering communications and professional practice, which included end-user computing, and I co-taught an integrated engineering design module, as well as managed the in-service training component. This experience gave me a bird's eye view of the challenges we still face in engineering education today. While working in the UOT space, I enrolled for my Master's in Higher Education Studies at UCT. I used the opportunity to interrogate the curriculum and our theory-practice bridging educational strategies. My in-service trainees couldn't see the connection between the preceding theoretical courses like material science and electronics and the latest automation technologies in simulated as well as industrial contexts. My industry partners, of whom I have a fairly extensive network, gave me invaluable feedback on general regarding higher education engineering graduates. And one complaint that was consistent was the student inability to work with rapidly evolving technologies in complex industrial contexts. So, having developed several responsive initiatives on the diploma programs, I then used my PhD and postdoctorate research periods to problematize what engineering practice in industry really looked like from a knowledge perspective. I did this using an entirely new language and set of instruments. At the heart of my work, I was trying to understand how engineering practitioners at different levels solved engineering problems in the real world at the interface between science, technology, society, and nature. Now, I used many useful tools from the sociology of education to look at learning and practice. One instrument is called the semantics dimension. Now, this is a way of linking abstract concepts to concrete contexts as we move from theory to practice within and across the curriculum. Connecting the dots is what Carl Mayton calls cumulative learning. Now, I've used this principle with engineering academics to really unpack the different levels of abstraction across different engineering disciplines. Doing this has helped them to see where their students have particular difficulties and how to link all the way from the principle of something down to the concrete, practical, real example and what those steps might entail. Now, the key instrument I used in my PhD research is called the epistemic plane. Now, the different quadrants represent insights, ways of thinking. Simply put, fixed, defined, or what we call strongly bounded phenomena with standardized methods, like most of the natural sciences, need what we call a purist insight. Now, we often call these things fundamentals or foundations or principles. Now, fixed procedures, irrespective of the concepts or phenomena, need iterative practice, and we call this requiring doctrinal insight, whether it's mathematics practice or handling specific kinds of tools. Now, when we move to the top left quadrant, we're talking about needing situational insight. Now, the phenomenon is clear, what we want to do, but there are multiple ways to do it. Now, the situation will dictate or guide decisions as to possible approaches. Now, this bottom left quadrant is about something other than knowledge. It's about context. Now, most of our university teaching happens on the right-hand side. Well, quite simply because it's easier to assess and it's more standardized. Now, what industry keeps asking for is graduates who can work on the left-hand side in the space of possibilities, where there are multiple possible approaches and where there are very different contextual features, different stakeholders. Now, what we do know is that real-world problem solving actually means code shifting, recognizing what kind of knowledge and what kind of practice you need at different moments in different contexts. Now, moving from fixed to open-ended approaches or from strongly to weakly bounded concepts, what we know is that we need to enable this kind of code shifting. Now here, working with my colleague Coral Kruger, he's used this epistemic plane to design and implement a strategy to improve control systems teaching, shifting between lab and virtual practice in a way to stretch students into more open-ended problem solving. There is another example of the use of the epistemic plane in a chemical engineering module. When mapped onto the epistemic plane, what we see is that this lecturer, my colleague Lydia Rett, explicitly enabled students to code shift from the conservation of mass and energy principles to the equations, to the use of software, bearing in mind the context of their specific projects. And she did this in an iterative, cumulative fashion. We've used the same principle of the epistemic plane to unpack the graduate attributes, as well as to design the student learner management system, the user interface, and how they're engaging with the different insights that they need. I've even used the plane to look into our students' experience of an enriched curriculum. Now, ways to expand our students' awareness of the rich contributions from our continent. Examples such as Samira Musa from Egypt, who developed the equation to break the atoms of cheap metals, making the medical applications of nuclear technology, such as X-rays, more accessible. Or Ibn al-Haytham. Now, he documented his use of the scientific method 700 years before Newton. Jamila Abbas, for example, from Kenya, saw that small-scale farmers were being taken advantage of based on their lack of bargaining power. She created a simple mobile phone platform to provide critical information to small-scale farmers so that they could organize themselves and pool their resources to act as commercial farmers, leveraging the advantages of commercial market positioning. Now, I've used these approaches and instruments and many more extensively in many ways in my own classroom, on engineering staff development across higher education institutional types. I designed 5 new engineering curricula for Stadio Higher Education. Now, this was a 2-year process in which I led a large team of academics and industry partners, and all 5 qualifications were endorsed by the Engineering Council. Now, this design process included the design of a fully integrated engineering learning environment. Now, my work with staff means taking the whole pipeline into consideration. Who are our students? What do we know? What data tells us what the challenges are? Where are the students going to? Where are our graduates? What do employers say? Not our advisory boards, supervisors and employers on the ground. What do our alumni say? We can't look at curriculum until we fully understand the context. Each higher education institution is different. What is possible in your institution? What resources are available? What is your higher education vision? And ultimately, what is the social context? And only when we have this kind of picture in mind, have engaged with these different stakeholders, only then do we zoom into the curriculum work, using cumulative learning principles to track how different forms of knowledge merge what we call epistemic transitions over time through a program into more integrated, holistic, real-world kinds of practices. Now, all of this kind of work takes time. This is not a quick Excel credit exercise. What it does lead to is a stronger community of practice. Now, in my Stellenbosch University and South African Society for Engineering Education context, for example, we have so many colleagues who have benefited in different ways through our regular engagements, workshops, collaborative projects. We have a thriving web practice sharing environment There have been promotions, publications, and real improvements in the classroom. So, all of this exposure, my work on the ground in real engineering classrooms, and my own research in industry has enabled me to work with colleagues across South Africa and internationally on different kinds of capacity building projects. And I'm hoping that I will be able to help you. Thank you.